700 million years ago, Earth ceased to be a blue marble and became a sterile, white marble of ice. This wasn't just a cold snap. It was a total planetary shutdown that locked the oceans in a frozen grip from pole to pole. The evidence is carved into the rocks beneath our feet, pointing to a world that shouldn't have recovered. Temperatures plummeted to -50 degrees Celsius, conditions so hostile they turned the equator into a polar waste. Yet, buried deep within the geologic record, we find signs that life did not vanish when the ice claimed the surface. How could any biological form maintain its metabolism when the sun's energy was reflected back into space by a continent-sized mirror of frost? This presents an immediate, impossible friction: the existence of microscopic, thriving life during an era where the surface was essentially a graveyard. We are left looking for the mechanism that kept the light of life burning in a world that had literally frozen shut. To understand how our planet survived this death grip, we must move beyond the surface-level geography and journey into the deep time of the Cryogenian, where we will begin to unearth the specific geological triggers that pushed Earth into the deep freeze, and the hidden forces that eventually shattered the ice. To unearth these triggers, we must examine Earth's structural integrity. The planet's crust was not fixed. Continents drifted, fractured, and rearranged, leaving the globe vulnerable to atmospheric starvation. This structural instability acted as a silent architect, setting the stage for a total collapse. To find the source of this precise geochemical trigger, we turn back the clock to 850 million years ago. Forces deep beneath the surface began to tear apart the supercontinent Rodinia, a vast landmass that had anchored the crust for hundreds of millions of years. This was not a slow-motion event. It was a continent-wide rupture that pushed vast, jagged tectonic blocks toward the equator. As Rodinia's fragmented landmasses migrated toward the equator, they exposed fresh, unweathered rock surfaces to the atmosphere. Clustered near the tropics, these new landforms occupied zones of highest rainfall and peak solar intensity. Here, moisture acted as a chemical catalyst, accelerating the erosion of silicate minerals from fresh volcanic rock exposed by the supercontinent's ongoing rifting. This process, known as chemical weathering, functioned like a sponge, systematically leaching carbon from the air to react with the exposed basaltic crust. Atmospheric carbon was locked into solid carbonates, effectively washing the planet's greenhouse blanket into the oceans. As these land masses drifted, the rate of carbon drawdown began to outpace Earth's ability to replenish CO2 through volcanic emission. This systematic scrubbing of warmth destabilized the climate balance, leaving the world vulnerable to a terminal cooling trend. The system was now primed for a reaction that would soon turn the rock-strewn surface into a frozen void. But what specific mineral interactions triggered this final, catastrophic collapse of our thermal defenses? This process relied on a chemical reaction known as silicate weathering. Basaltic rock, abundant across these fractured tropical plates, acts as a potent sink for carbon dioxide. As rainfall, naturally acidic from dissolved CO2, washed over these exposed surfaces, it chemically dismantled the volcanic minerals. This interaction converted gaseous carbon into dissolved bicarbonate ions, which were then transported by runoff into the world's oceans. Once in the sea, these ions combined with calcium to form solid carbonate deposits on the ocean floor, effectively burying the carbon away from the atmosphere. Earth usually keeps its thermal balance through volcanic outgassing, which injects fresh CO2 into the air to replace what the rain leaches away. But the specific positioning of these continental fragments meant the rate of mineral dissolution surged beyond the speed of volcanic replenishment. The planet was systematically scrubbing its own blanket of warmth, continuously locked in a cycle of carbon extraction that no geological counterprocess could check. The climate's natural thermostat had failed, and as the atmosphere began to lose its capacity to retain heat, the global temperature curve entered its final, steep descent. What would happen when this atmospheric deficit reached the point where the first permanent ice sheets began to expand? As this atmospheric deficit grew, the poles became engines of subtraction. Polar ice ceased its seasonal retreat and began a relentless migration toward the mid-latitudes, physically altering the planet's surface. Where once dark oceans and exposed rock soaked up the sun's warmth, a blinding white barrier now took hold. Once the ice sheets crept past 30 degrees latitude, the planet's albedo took control. Dark oceans that once absorbed solar radiation were replaced by white glaciers, repelling heat back into the void. This thermal shift turned Earth into a thermodynamic trap. The cooling was no longer a sluggish byproduct of changing atmospheric chemistry. It was now a runaway reaction driven by the Earth's own geometry, the runaway ice albedo feedback loop. The climate, once responsive, was locked in a cycle where every additional square kilometer of ice accelerated the descent. The geological record confirms this reached the tropics, turning the entire planet into a rigid, energy-starved sphere. Yet, this absolute lockdown creates a deeper dilemma. If the oceans and land masses were driven into a state where even equatorial seas were choked by ice, the climate was effectively switched off. The physics of this deep freeze leave us with an unresolved critical question. What invisible force could possibly break such an ironclad grip and reverse a total planetary lockdown once it began? We have to look toward the planet's hidden, subterranean engines to find the answer. That heat engine in the mantle continued its relentless grind, indifferent to the absolute silence above. Even under kilometers of ice, plate tectonics forced volcanic arcs to pierce the surface. These vents became a singular conduit, pumping plumes of carbon dioxide into an atmosphere that had lost its primary drainage system. With the oceans sealed tight by the global freeze, the carbon had nowhere to dissolve, forcing it to concentrate in the thin, frigid air. This accumulation was a slow-motion transformation of the planet's chemistry. Over millions of years, the atmosphere morphed into a pressurized, greenhouse gas-rich blanket, storing potential energy that the runaway feedback loops could no longer suppress. This subterranean buildup was the only mechanism capable of challenging the icy grip. Yet it remained invisible, a ticking clock of rising heat hidden beneath a white, deathly shroud. This chemical spike led to the first definitive, systemic collapse of the era. The evidence of this initial, absolute lockdown remains etched into the rock layers of the Sturtian glaciation, waiting for us to uncover how exactly the world shifted from tomb to transition. This geological record reveals an era of dynamic, violent environmental shifts rather than a stagnant block of ice. Sedimentary data indicates the Sturtian episode involved continuous planetary oscillations. During this expanse, the planet did not merely sit dormant. It fluctuated between a total equatorial freeze and periods of relative thinning, creating a volatile planetary seesaw. This instability acted as an unforgiving filter, forcing microbial life to endure massive, long-term dormancy, interrupted by brief, chaotic pulses of warmth. These physical signatures are scattered across the modern globe in patterns that defy random chance. They are the only survivors of that silent, frozen epoch, yet identifying the specific footprints of these glaciers when the landscape has been ground down by hundreds of millions of years of tectonic movement requires a new way of seeing. The challenge lies in isolating evidence that has been physically mangled by the weight of time, leaving geologists to look for signs that shouldn't exist in the tropics at all. But just what are these markers that force a total re-evaluation of Earth's frozen history? These markers are physically etched into the planet's crust. Deep within sedimentary layers, geologists found massive, poorly sorted deposits known as tillites, compressed debris of boulders, pebbles, and fine silt ground together by the force of moving ice. In modern contexts, these formations appear only at the base of active glaciers. Yet, paleomagnetic data tracks these specific strata back to the equatorial belt. It is a record of rock scraped and deposited by ice while located under the tropical sun. More telling still are the dropstones. These are large errata rocks embedded in fine-grained marine sediment. They exist because icebergs broke from glaciers and drifted across the ocean. As the ice decayed, the trapped boulders tumbled down, punching through the soft, silty seafloor. Finding an out-of-place boulder embedded in prehistoric deep-sea shale is a direct, tangible record of a frozen sea. The presence of equatorial icebergs confirms the scale of the crisis. It was not a regional climate anomaly. It was a complete atmospheric collapse, holding the Earth in a terminal, crystalline vice for millions of years. The scientific consensus once insisted that glaciers were confined to high latitudes, leaving the tropics a perpetual, sun-drenched sanctuary. That certainty fractured in 1964 when British geologist W. Brian Harland presented data that forced a total re-evaluation of the Cryogenian. By analyzing the magnetic orientation of minerals locked inside ancient sedimentary strata from Svalbard and Greenland, he identified the signature of glacial movement at latitudes that were, at the time of their formation, positioned firmly near the equator. The magnetic field recorded in those rocks acted as a physical coordinate, placing equatorial landmasses directly beneath the weight of ice sheets. Though his findings were initially dismissed as an error in field technique or a radical outlier, global cross-referencing of these deposits soon silenced the skepticism. The rock record confirmed that glaciers had indeed clawed their way into the most tropical zones of the planet. This evidence stripped away the final defenses of a moderate climate model, leaving only the stark reality of a global deep freeze. Yet, as geologists accept that ice reached the equator, the sheer duration of these frozen states creates an unsettling riddle. How long did the Earth remain locked in this state? And what does that timescale reveal about the planet's survival? To understand the scale of these glaciations, one must abandon the standard human perception of climate as a series of seasonal or even millennial shifts. We are looking at a planetary deep freeze that operated on a scale of tens of millions of years. The Sturtian glaciation alone endured for roughly 56 million years. To visualize this duration, consider that the entire span of human evolution, from the first hominids to the present day, is a fleeting blink compared to the half-century of millions of years that the Earth spent entombed in white. This wasn't a static event either. Geological records now suggest that these long intervals were punctuated by rapid oscillations between the absolute deep freeze and shorter, warmer intervals of hothouse conditions. The planet was essentially flickering in a state of violent instability, swinging between extremes with a sluggish tectonic rhythm. This suggests the climate system was caught in a feedback loop so severe it could not find a middle ground, repeatedly crashing and resetting its own planetary thermostat. But if these ice-bound epochs were a recurring failure of the Earth's climate, the geological record begs a far more difficult question. Were these events truly unique to the Cryogenian? Or did this frozen instability have an even deeper, hidden history buried beneath the reach of our current timelines? The answer lies deeper, pushed back into the Proterozoic era, roughly 22 billion years ago. Long before the Cryogenian ice locked the continents, a predecessor event, the Maganian glaciation, scoured the world. Glacial tillites discovered in South Africa provide silent evidence that this extreme planetary state was not a singular accident, but a recurring failure of the climate system. The timing of this earlier event coincides with the Great Oxidation event, a massive rise in atmospheric oxygen that stripped the air of methane. With that greenhouse blanket pulled away, surface temperatures plummeted. This establishes that these global freezes were a systemic vulnerability, not a one-time crisis. The geological record confirms that the planet possessed a volatile internal thermostat, one capable of plunging into a deep freeze long before the emergence of complex life. Yet, as geologists analyzed the transition out of these ancient freezes, they noticed an anomaly. Resting directly on top of these glacial deposits, a layer of rock appears that seems entirely disconnected from the cold that preceded it. A strange global signature that defies a simple explanation. These rock beds, known as cap carbonates, occur globally, forming a sharp, distinct boundary right where the ice vanishes. They are chemically unusual, composed of limestone or dolomite that, under normal conditions, would only precipitate in warm, shallow tropical seas. Finding these thick, pervasive carbonate layers draped directly over deep-frozen glacial tillites is a geological contradiction. It suggests an instant transition from a global deep freeze to a greenhouse climate that was intense enough to force rapid, massive chemical precipitation across every ocean basin. The physical layering is so sudden, it implies a violent change in seawater chemistry. An abrupt, global shift that occurred within a mere geological heartbeat. These layers lack the diverse skeletal fossils of later eras. Instead, they display cryptic, crystalline structures that point toward a high-stress ocean environment struggling to recover its balance. They are the chemical diary of a planetary pulse, documenting a violent shift in the carbonate-silicate cycle. That remains one of the most enigmatic chapters in the geological record. But the mystery deepens when we turn to the marine fossils encased within these strata. Further deep-time clues emerged from the ancient oceans, pointing to a world where the water itself had fundamentally changed. Within these sedimentary records lie banded iron formations, rhythmic, layered deposits of iron oxides and chert that appear in the geologic record only when oceans suffer total, systemic oxygen depletion. Under normal conditions, iron remains locked away in solid minerals on the seafloor. But when the entire global ocean is cut off from the atmosphere by a sealed lid of ice, the water chemistry shifts. Without oxygen to react with, iron leaches into the depths, building up in concentrations that shouldn't be possible in a healthy, aerated sea. These layers serve as a chemical record of anoxia, marking the exact moments when the world's oceans stagnated into a toxic, lifeless broth. They confirm that the freeze was not merely a surface event. It was a total breakdown of the Earth's life-sustaining circulation, leaving the deep oceans entirely isolated from the cycles of the sun and the sky above. As the ice thickened over these starved seas, the sheer, crushing load began to deform the planet's very foundation. Under the weight of kilometers-thick ice sheets, the lithosphere, Earth's rigid outer shell, deflected downward. This was not a localized event, but a total, global deformation of the planetary crust. Entire continental blocks were pushed deeper into the mantle, forced by the unrelenting gravity of millions of years of ice accumulation. Geologically, this is known as isostatic depression, a process where the Earth acts not as a solid stone, but as a fluid body responding to a shifting, temporary burden. The mass was so extreme that it altered the local stresses within the crustal rock itself. Deep-seated faults, dormant for eons, felt the strain of this planetary compression. Scientists mapping ancient cratonic basins observe signatures of this structural buckling, revealing that the planet was physically distorted, squeezed like a ball held in a tightening grip. This represents a fundamental change in Earth's tectonic energy balance, creating a state of perpetual, hidden stress that would persist long after the ice vanished. But what happens to the land when that weight is suddenly lifted, and the crust attempts to reclaim its original shape? The sudden removal of that icy burden triggers a planetary reflex known as post-glacial rebound. As the ice vanishes, the lithosphere does not simply snap back. It struggles to attain equilibrium. The land masses begin a slow, protracted rise, an upward migration that can persist for millions of years. This tectonic respiration generates localized earthquakes. As long dormant faults groan under the release of stored strain, and it permanently shifts sea level shorelines across the globe. These redirected coastlines remain visible to modern geologists, acting as a lithospheric archive of the weight that once nearly crushed the world. The crust behaves like a compressed spring held for epochs, only to be released in an uneven, chaotic redistribution of mass that alters drainage patterns and regional volcanic activity. Yet, even as the tectonic plates fight to stabilize, the primary challenge remains: how to prove such a global lockdown actually occurred. The evidence lay scattered in Greenland, Svalbard, and Africa, waiting for a framework that could unite these disparate, frozen clues into a singular, undeniable reality. This required a radical shift in perspective, one that would finally force the scientific community to confront the ghost of a frozen world that most researchers, until the late 20th century, simply refused to believe could exist. In 1992, geophysicist Joseph Kirschvink broke the scientific stalemate. He transformed Harlan's fragmented glacial evidence into a rigorous, mathematically defensible model of total system failure. Kirschvink demonstrated that the planet's cooling was not a series of isolated anomalies, but the result of a runaway ice albedo feedback loop. He calculated that once sea ice crossed the 30-degree latitude threshold, the process became irreversible, dragging the entire globe into a terminal, pole-to-pole freeze within a geological blink of an eye. This framework shifted the debate from regional glaciations to a state of absolute planetary collapse. He challenged the scientific community to explain how the world remained geologically active beneath kilometers of ice, asking, if the planet were truly sealed in a cryotom, what internal force could possibly build enough pressure to shatter such a massive, frozen cage? The answer to that pressure resides in the planet's refusal to stop breathing. Even as surface oceans locked behind miles of ice, Earth's mantle remained active. Subterranean volcanoes continued their cycle, venting carbon dioxide into the stagnant space between the lithosphere and the ice shield. With no open ocean to absorb this byproduct, gas levels skyrocketed, turning the atmosphere into a pressurized greenhouse reservoir. Kirschvink's model defined this mechanism. Ending a deep freeze required no external heat, but the calculated accumulation of internal waste. This geochemical pressure cooker eventually forced the ice to thin, allowing sunlight to penetrate and ignite the terminal melt. This shifted our perception of Earth from a static rock to a self-correcting machine, where the very chemistry that triggered the disaster acted as the agent for its destruction. The geological record, once viewed as a series of isolated anomalies, snapped into focus as a rhythmic cycle of extinction and renewal. This persistent volcanic carbon buildup finally pushed the global climate past the point of no return, with this massive surge of heat finally shattering the grip of the ice. We are left to confront the most resilient survivors of Earth's history. For millions of years, the world was a locked, light-starved vault. Any life forms persisting through these millennia had to survive in total darkness or extreme isolation, detached from the typical energy cycles of the surface. Scientists now recognize that this was not merely a passive state of hibernation, but an active, brutal evolutionary filter. Microscopic organisms, including the resilient ancestors of our own complex biology, were forced into specific, extreme refugia. These hidden zones were the only places where metabolic processes could continue, while the planet's crust groaned under the weight of glaciers. But these refugia remain a point of heated debate, as experts work to trace the precise, localized conditions that allowed life to endure while the global climate failed. The focus narrows to the Franklin Large Igneous Province, a massive volcanic expanse in northern Canada. This was no ordinary geologic event. It was a violent rupture of the crust. As this massive province spewed molten basalt across the surface 717 million years ago, it exposed vast quantities of fresh, reactive rock to the atmosphere. Torrential tropical rains began a relentless, accelerated cycle of chemical weathering, stripping carbon dioxide from the air and locking it away in marine sediments. The planet's primary greenhouse gas, essential for maintaining global warmth, was being scavenged at a rate the Earth's natural volcanic output could not replace. This massive geochemical drain effectively flipped the planetary thermostat to permanent frost. Yet, even as this cold pulse locked the world in ice, the sheer intensity of the freeze presented a lethal paradox for the tiny organisms trapped in the cooling oceans. If the physical conditions were truly as absolute as this geological record suggests, one remains forced to wonder, how could the most fragile forms of life persist? Survival was not a matter of choice, but of biological persistence under an uncompromising filter. These organisms, primarily cyanobacteria and nascent eukaryotes, were already masters of cellular repair, a trait honed by billions of years of solar exposure. Now, they were pushed into restricted zones of light and chemical energy. For the photosynthetic pioneers, the thickness of the ice sheet became the primary arbiter of life. In regions where the ice grew thin enough to allow for the penetration of solar radiation, these microbes thrived in the frigid surface waters. This limited light was sufficient to fuel their fundamental metabolic processes. Yet, the geography of this survival remains a subject of intense investigation. The critical question for paleobiologists is whether these habitats were truly isolated, or if the entire ocean functioned as a connected, albeit sluggish, biological network. This debate hinges on the exact physical state of the frozen ocean, a topic that has sparked a divide among researchers for decades. Was the Earth a fully sealed, static tomb, or did it maintain a more dynamic, liquid, accessible geometry that we are only now beginning to model? The validity of this split in scientific opinion rests on the limits of current climate modeling. If the global ocean was a rigid, multi-kilometer slab of ice, gas exchange between the atmosphere and the water column would have effectively ceased. This would create a stagnant, oxygen-starved ocean, forcing life into absolute, localized dependence on seafloor processes. Conversely, if equatorial regions remained even partially liquid, the ocean would function as a vast, continuous habitat, allowing nutrients to cycle beneath a fractured, shifting skin of ice. This slush ball hypothesis implies the global climate was never as binary as early research assumed. Instead, the Earth likely oscillated through transient states, with thin, translucent ice allowing solar energy to penetrate the upper water column. This changes the survival parameters for early life. If organisms were not restricted to isolated, lightless depths, they could have maintained a tenuous, sun-linked presence throughout the glacial cycle. Yet even with these potential environmental compromises, the surface remained a lethal, unforgiving filter. Survival depended entirely on identifying specific, fleeting pockets of liquid space within a planet-wide waste. These potential sanctuaries represent the only thin margin where life managed to hold its ground. These surface meltwater ponds served as primary staging grounds for a fragile, light-dependent resistance. During the height of the summer cycles, even in the deep equatorial regions, local solar heating generated thin layers of liquid water atop the multi-kilometer ice sheet. These ephemeral pools were not stagnant voids. They acted as biological lenses, focusing enough solar radiation to sustain clusters of cyanobacteria. Within these narrow, sunlight-saturated windows, microbial populations were able to maintain photosynthesis, effectively harvesting energy, despite the global sub-zero ambient temperatures. But these ponds were physically precarious, subject to constant freezing and seasonal shifts that threatened to entomb or crush whatever life had gained a foothold. The survival of these communities was not just a result of mere existence, but of their ability to synchronize their metabolic rhythms with these fleeting, high-energy pulses. However, the surface was only one part of the equation. Beyond these ponds, where the ice sheets met the surrounding crust, a different, more continuous source of water began to emerge. The next stage of survival required life to tap into the turbulent, oxygenated currents draining from these glacial edges, where nutrients were stripped directly from the raw, exposed rock. These oxygenated corridors acted as vital arteries for an otherwise paralyzed biosphere. As glacial meltwater scoured the pulverized rock beneath the ice edge, it liberated trapped mineral nutrients, phosphorus, iron, and silica, releasing them into these turbulent liquid zones. For microscopic life, this was an injection of raw, chemical fuel. This runoff provided more than just a place to live. It acted as a liquid filter, concentrating essential elements that were locked away in the ice. In these churning, silt-laden waters, microbial communities developed localized, high-energy hotspots of metabolic activity, flourishing in the shadows of the massive sheets. This constant movement prevented the waters from turning stagnant, sustaining oxygen levels that might have otherwise vanished in a closed system. Yet, these surface-level oases were still beholden to the caprice of sunlight. As the ice sheets thickened, the penetration of light would have become fatally inconsistent, threatening the very engine that powered this survival. If these sun-dependent corridors were eventually swallowed by the encroaching freeze, it forces us to wonder if life had an alternative strategy. A way to bypass the sun entirely to thrive in the permanent darkness of the deep. Beyond the surface, the abyssal silence of the ocean floor offered another refuge. Here, far beneath the crushing weight of the ice-locked water column, the Earth's internal furnace remained lit. Scattered along mid-ocean ridges, hydrothermal vents acted as localized thermal engines, bleeding superheated, mineral-rich fluids into the frigid depths, while the rest of the planet succumbed to the sterile grip of the deep freeze. These chimneys sustained isolated, chemical-based ecosystems. Unlike surface organisms tethered to the thinning, failing rays of the sun, these microbial communities utilized chemosynthesis, harvesting energy directly from the volatile chemical cocktails erupting from the crust. It was a subterranean vitality, fueled by the planet's tectonic core rather than the radiation of a distant star. By uncoupling their survival from the atmosphere, these organisms successfully bypassed the global extinction pressure, turning the deep sea into an impenetrable vault for life. These organisms had effectively turned the planet into an evolutionary laboratory, forcing life to survive not through expansion, but through absolute isolation. This genetic and metabolic bottleneck stripped away inefficient biological traits, leaving only the most durable, resilient blueprints. Deep-sea microbes, specifically those flourishing near hydrothermal vents, developed specialized pathways for processing geothermal heat and minerals, that were entirely severed from the surface world. This isolation was a crucible. When global conditions finally shifted, these lineages were not merely surviving. They were primed to exploit a radically altered chemical environment. By maintaining a continuous link to the Earth's inner heat, they bypassed the surface's total biological collapse. This survival was not a stroke of luck, but a consequence of life's ability to anchor itself to the planet's geological pulse, ensuring the fundamental machinery of biology persisted through the most punishing environmental filter in history. The thread was preserved, and in its enduring strength, it held the genetic potential for everything that would emerge in the subsequent eons, proving that life could survive even when its home planet turned against it. While life waited in these isolated pockets, the planet's internal engines remained oblivious to the ice. Plate tectonics continued its slow, grinding movement, dragging vast continental blocks across the mantle. Subduction zones pulled carbon-rich sediments deep into the Earth's searing interior, heating them until they melted into magma. This wasn't merely a movement of rock, but a gargantuan recycling mechanism that operated in complete, silent isolation, far below the miles of frozen ocean. The lithosphere fractured and shifted, driven by the heat of the planet's core. The mantle plumes, rising from the deep, sought release through the thinning crust. Every tectonic collision and every continental shift served to generate immense pressure, building a reservoir of volcanic heat and gas that had no exit route. This geological clockwork was blind to the frozen surface, but it didn't stop. Below the ice, tectonic plates continued their slow, grinding migration, dragging volcanic arcs and massive rift zones across the mantle. These vents and fissures acted as constant valves, pumping carbon dioxide into the stagnant pockets of the atmosphere trapped beneath the kilometer-thick ice sheets. With no liquid oceans to scrub the gas from the air, the concentration began to climb. It was a planetary pressure cooker. The basaltic crust beneath these vents became a chemical laboratory, leaching minerals that saturated the trapped waters and altered the balance of acidity across the sea floor. This wasn't merely heat venting into the void. It was a silent, chemical accumulation that started to alter the very composition of the atmosphere. This building gas was still a prisoner of the ice, but the critical tension now rested on a single prospect. Would the gas buildup reach the tipping point before the planet remained locked in its frozen state permanently? Without liquid oceans to act as a global carbon sink, CO2 concentrations surged. Paleoclimatic models estimate that atmospheric levels needed to rise to hundreds of times modern values to force a thaw, a slow-motion chemical assault on the cryosphere. Volcanoes, largely fed by subduction zones and mantle plumes, continued to pump gas through the crust with unwavering tectonic indifference. This volcanic forcing turned the Earth into an experimental, high-pressure laboratory. As carbon steadily filled the atmosphere, it created a silent, thickening insulation. The surface remained trapped in a deep freeze, but the heat energy reflected by this expanding greenhouse blanket began to destabilize the base of the ice sheets. The planet sat on a volatile, invisible trigger, but the question remained. Would this thermal buildup eventually break the icy armor, or would the system enter a final, irreversible lockdown? The answer arrived not in a gradual warm-up, but through a volatile, multi-stage failure of the planetary seal. as volcanic carbon dioxide concentration climbed past the atmospheric threshold, reaching levels hundreds of times greater than today. The sheer density of the greenhouse blanket began to override the ice albedo reflex. Yet this transition was not a simple melting. Geological signals indicate the climate entered a state of rapid, violent oscillation. Massive surges of infrared heat trapped beneath the dense atmosphere began to stress the base of the ice sheets, liquefying them from the bottom up. As the pressure of these subglacial reservoirs grew, the crust itself responded, straining against the heavy load before the entire system fractured. This was the thermal tipping point. The runaway feedback cycle didn't just stop. It inverted with catastrophic speed, triggering a period of global warming so swift it redefined the terrestrial climate. This collapse finally shattered the deep freeze grip, but it also left the Earth vulnerable to a final closing act of the Cryogenian drama. The retreat of the Sturtian ice was merely the first phase. There was one more, even more extreme ordeal that the planet had to endure. The Marinoan glaciation stands as the final, brutal act of the Cryogenian theater, a freeze that descended rapidly around 650 million years ago. While the previous Sturtian episode set the stage, the Marinoan event pushed the planet to the very edge of biological erasure. This period was likely shorter than its predecessor, clocking in at perhaps 6 to 12 million years. But its grip was no less absolute. Sedimentary records across the globe show a distinct geological hiatus during this time, a silent gap where the planet effectively ceased its active surface chemistry. Glacial tillites from this phase blanket the continents in a consistent, unrelenting layer of debris, documenting a world where even the most resilient microbial refugia were forced into a near-total metabolic suspension. The geological evidence suggests that just as the climate system reached its peak of instability, the internal engines of the Earth had to overcome a new, more lethal barrier to trigger the ultimate return to warmth. The ice had become so thick and the albedo so high that the planet could not simply shift back to a temperate state. It required a total systemic failure of the carbon cycle. This set the stage for a thaw defined by such violence that the very crust of the planet would be fundamentally reconfigured by the sudden release of pressure. The hydrological scale of this transition was unmatched in Earth's history. As the greenhouse threshold was crossed, the multi-kilometer ice sheets did not merely evaporate, they shattered. The rapid release of this stored potential energy surged into basins as meltwater, creating floods that scoured mountain ranges and stripped default to the core. This deluge flushed massive volumes of pulverized sediment into the sea in a geological heartbeat. Such an influx of freshwater decimated oceanic salinity, inducing a radical stratification of marine layers that seized all deep-sea circulation. The seafloor became a stagnant, anoxic trap, while coastlines were battered by unprecedented sea level rise as locked water returned to the basins. This sudden redistribution of mass-strained tectonic fault lines, triggering seismic instabilities as the crust snapped upward through violent isostatic readjustment. Beneath this physical chaos, the oceans became a volatile, supersaturated brew of dissolved minerals and concentrated chemical elements. This transition set the stage for an immediate and transformative chemical reaction. one that would cement the planet's future in stone. We must now identify the precise mechanism that enabled this rapid influx of minerals to forge the signature rock layers that followed the thaw. As the ice retreated, the geochemistry of the oceans underwent a violent, near-instantaneous shift. The extreme weathering of silicate minerals, suddenly liberated from their glacial shroud, dumped enormous quantities of calcium and bicarbonate into a thirsty, stagnant ocean. In this hypersaline, mineral-rich soup, the saturation levels hit a tipping point. Carbonate minerals didn't just settle gradually. They precipitated out of the water column in a massive global chemical event. This rapid-fire precipitation forged those signature cap carbonate layers, acting as a stony record of the planet's sudden return to a high-energy alkaline state. This was not a long, drawn-out cooling transition, but a sudden, chaotic rebound in ocean chemistry that essentially cauterized the end of the Cryogenian. These layers, ranging from a few meters to hundreds of meters thick, display peculiar structures, crystal fans and ripples that indicate they formed in a turbulent, high-energy environment directly following the thaw. These rocks are the geological final punctuation mark on the frozen era, confirming that the planet's recovery was as extreme and unforgiving as the lockdown itself. With the cap carbonates settling, the Earth finally stabilized, its geochemical cycle resetting as it stepped into a vastly different and soon-to-be biological future. This extreme filtering mechanism favored life that could thrive under high stress, pushing microbial populations to diversify their metabolic strategies. Before the thaw, life was trapped in a state of stagnant survival, forced to scavenge minerals in isolation. Now, the planet's crust and oceans were surging with a volatile chemical mixture, creating an environmental catalyst that had never existed before. This was not a slow transition. It was a rapid, involuntary migration toward more energy-intensive lifestyles. The sudden shift in ocean chemistry, driven by the rapid dissolution of carbonate minerals and the influx of weathered landborne ions, created a highly reactive environment. As the old, stable, and simple systems collapsed, the stage was set for a fundamental change in the scale of life itself. The bottleneck forced an evolutionary trade-off. Organisms that could better utilize this influx of raw, reactive material would outcompete those that remained stagnant. A new complex interplay was about to begin, but the critical question remains. What was the specific spark that allowed life to exploit these volatile waters and finally break the microscopic barrier? The spark was a sudden surge of weathered minerals, flushed into the ocean from newly exposed land masses. As the ice retreated, it left behind pulverized rock dust, dense with phosphorus and iron. This geologic debris acted like a planetary fertilizer. When sunlight hit the open water, cyanobacteria, which had persisted in stagnant, deep-sea refugia, exploded into a bloom of global proportions. This was a rapid, violent shift in ocean productivity. The scale of this algal growth overwhelmed the local carbon cycle, forcing a total reorganization of marine water chemistry. This massive biomass processed carbon at a rate never before seen, creating a feedback loop where biological dominance required increasingly refined survival strategies. Organisms began to specialize as the chemistry of their environment pivoted from nutrient-starved to hyperactive and reactive. The massive byproduct of this photosynthetic boom was a global shift in oxygen saturation. This influx of oxygen fundamentally altered the energetic landscape of the oceans, leaving the next evolutionary step to be defined. This oxygen surge acted as a physiological catalyst, shattering the barriers that kept life locked in simple, single-celled states for billions of years. With oceanic oxygen levels spiking, organisms unlocked more efficient aerobic metabolic pathways, generating the massive energy surplus required to fuel complex genetic transcription. Life moved beyond basic replication. Cells began to specialize, differentiating into tissues capable of coordinated action that was physically impossible in a frozen, stagnant world. Ecosystems evolved from static microbial mats into dynamic, tiered food webs defined by predation and consumption. The biological architecture of Earth was fundamentally redesigned. The fossil record captures this transition as the post-glacial landscape began to teem with the first true macroscopic, multicellular inhabitants. We are witnessing the arrival of the Ediacaran biota, enigmatic, soft-bodied pioneers of an entirely new chapter. Their sudden emergence forces a central, unresolved question. How exactly did these complex organisms manage to coalesce in the immediate wake of such a planetary cataclysm? The Ediacaran biota did not arrive via a slow, gradual crawl. They appear abruptly in the fossil record, exhibiting forms that defy classification into any living animal phylum. Some grew over 1 meter long, leaving impressions in fine-grained sandstones that reveal a distinctive, quilted geometry. Lacking appendages or traditional sensory organs, these organisms occupied niches that imply a surprisingly tiered ecological structure. They absorbed nutrients through massive surface areas, thriving in a marine environment finally stabilized by the massive influx of alkalinity and minerals during the post-freeze carbonate precipitation. This surge in ocean chemistry provided the high-energy substrate required for cellular specialization. This rapid diversification suggests these complex body plans were either a direct adaptation to the post-snowball biosphere or a latent capability held in check for eons. Their existence pushes the timeline for animal life far deeper into the past than once suspected. Yet, the leap from these static forms to the mobile, armored fauna of the Cambrian period remains a volatile mystery. Were these Ediacaran pioneers an essential evolutionary bridge, or simply a biological experiment that pushed life to its absolute limit? These soft-bodied pioneers were the final, fragile output of the planet's Great Freeze, acting as a biological archive of that survival. The Cryogenian period was not merely an ice age. It was a selective pressure cooker. To endure millions of years sequestered in the dark, life was forced to rewrite its genetic manual, favoring organisms that could manage complex internal signaling and rapid metabolic switching. This era functioned as a cold-blooded filter, stripping away vulnerable strains and leaving only those with the plasticity to exploit the sudden, nutrient-rich seas created by the post-glacial melt. When the terminal heat pulse shattered the ice, the infusion of phosphorus and iron into newly oxygenated, alkaline oceans catalyzed a frenzy of growth. Single-celled clusters were forced into higher degrees of cooperation, scaling up from simple aggregates to organized, tiered architectures. The thread of life was not severed by the bottleneck. It was sharpened. This transition explains the sudden surge into complex animal form. Yet it raises a new, lingering tension. How did the planet's geochemical systems move from that volatile, post-freeze collapse toward the delicate, steady state required to sustain this emerging complexity? This transition required a fundamental shift in how the planet scrubbed carbon from its atmosphere. The geochemical system moved from the rapid, chaotic pulse of the post-thaw era toward the more stable, slower-burning cycle we inhabit today. The mechanism driving this stabilization was the massive burial of organic carbon within seafloor sediments, effectively sequestering the greenhouse gases that had ballooned during the deep freeze. This sequestration process was accelerated by the weathering of new, nutrient-rich mountains pushed up during the violent crustal rebound, which acted as a long-term sink for atmospheric carbon. By locking these biological remnants beneath layers of silt and stone, the Earth engineered its own greenhouse thermostat, creating a durable, temperate environment. Our current climate rhythms are tethered to the very feedback loops that once dominated the Cryogenian, proving that the planet not only survived a total lockdown, but learned how to regulate its own survival. These feedback loops are not historical relics, but the blueprints for modern planetary stability. Every orbital shift or volcanic pulse echoes that ancient Cryogenian struggle. Our climate thermostat is the direct successor to the geochemical and biological adaptations crystallized during millions of years in the deep freeze. We inhabit the relative calm following those ice age storms, perched on a system that has repeatedly proven its capacity to swing toward a terminal, global state. By analyzing deep time records from Greenland's cliffs and South African plains, scientists map the literal survival threshold of our own evolutionary trajectory. Earth is a system in constant negotiation, cycling through near extinction to drive biological innovation. We owe our biosphere to those icy crucibles. And as the scientific community measures the fragility of our modern climate, those ancient, frozen rocks remain the most empirical evidence of our planet's future range of motion.